the colloquium today, and today we are very happy to have Mahmoud Asmar from a little bit northwest from Atlanta, still in Atlanta, to visit us and give a talk on his research. So let me briefly introduce Mahmoud. So he got his PhD from Ohio University in 2015, and then later do a postdoc at the University of Alabama and Louisiana State University before he joined Kennesaw State. And he's an expert in a few topics in condensed matter theory, including periodically driven system that he's going to talk about today, and also low-dimensional system and topological basics, which are very hot topics in condensed matter theory. So please welcome Mahmoud.
Thank you very much, and thank you for the introduction, and thank you for having me at Georgia State. So today I'm going to talk about a specific topic, which is the photo control of quantum matter. The first topic that we're going to deal with today is something called Dirac-like materials, including two-dimensional materials, specifically graphene and topological insulators. And then as a physical phenomena that I'm going to be focusing on in this talk, for the purpose of this talk, I'm going to talk about the indirect exchange interaction, or the RKKY interaction and its control. Then in the following parts, I'm going to show you how we can have a photo control or a control through periodic driving of this type of phenomena. So let's dive into the materials immediately, right? So the first thing that we do is the materials. So let's start with Dirac-like materials or Dirac materials. So any material that has low energy quasi-particle excitations, basically quasi-electrons, because in materials we do not have real electrons, we have quasi-electrons, right? So any material that has low energy electrons that are described either by a massless or a massive Dirac equation, we call it a Dirac-like material or a Dirac material. So these materials usually are present in 2 dimensions or in 3 dimensions. In 2 dimensions, we have the famous examples of graphene. The first example, this was the first 2-dimensional material that was achieved. And as you can notice, this material is what we call a semi-metal, and it has a massless Dirac dispersion in its Bragg zone. So the effective low-energy quasi-particles are massless Dirac fermions. After the discovery of graphene, we discovered also the family of the transition metal dichalcogenides, and the most famous amongst is molybdenum disulfide. Unlike graphene, which is a semi-metal, molybdenum disulfide is a semiconductor, and this is described by a massive Dirac equation. So in this case, we have a gap, basically the distance between a valence and a conduction band, that's in the order of 1 to 3 electron volts. We also have insulators. So hexaboron nitride, which is also a 2-dimensional material, right, is described by a massive Dirac equation, but now the gap is much, much larger. It's of the order of 6 electron volts, making it an insulator. So we have these Dirac materials in 2 dimensions that can come in different states, electronic states, semi-metal, semiconductor, and insulator. So now, why is graphene so special? Why are these 2D materials so special? How do these low-energy quasi-particles that are almost relativistic appearing in a material, right? So let's go to basics of materials, right, or solid state. This is a lattice of graphene, is a honeycomb arrangement of carbon atoms. This is not a Bravais lattice. That means that I don't have a single set of discrete translations that can generate this whole configuration by once. I need 2 sets of them. We call that the basis of graphene. So even though the atoms are carbon, I have a set of bases that I call A and another set of bases that I call B. So in reality, graphene is 2 lattices, 2 triangular lattices that are overimposed on top of each other. Okay? So the orange lattice, if you follow, I have a triangular lattice in the orange side, and on the yellow side, I also have another triangular lattice, and I overimpose them and they form graphene. So I have the need to have bases to describe graphene. First 2-dimensional material that was discovered, and it was discovered in the most interesting of ways, through Scotch tape. You Scotch tape it, you deposit it, you find graphene. You don't need something more sophisticated than that. It's composed of carbon atoms, and it's in an arrangement that it's not a Bravais lattice. This is fundamental for its description. If we're going to talk about the orbitals, in the plane, graphene is extremely strong. And that's because what keeps the plane stable is the sp2 hybridization of the orbitals. Whatever is left in the from these orbitals is the pz orbital that sticks out of the plane. These pz orbitals are the ones that are responsible for the conductions of electrons in graphene. As soon as there is a tiny overlap between these orbitals, my electrons can hop from side to side. And this is why the tight binding model, which assumes that an electron can jump from side to side, whatever is created here is annihilated from the nearest neighbor side, is a very good model to describe this type of material. It's a very simple method, but it works extremely good because of this fact of the highly localized pz orbitals. Now, this will lead to very unusual properties. The geometry plus the orbitals, basically the tight binding type of description of graphene, will lead to very interesting properties. I'll save you the details of the tight binding Hamiltonian. Assume we can write it, then we can diagonalize it. We find the dispersion relation, basically how energy versus momentum looks in my Brillouin zone. Remember, if we have a real space that's periodic, my reciprocal space is periodic, and the smallest portion of that momentum space we call a Brillouin zone, just as a definition. So we diagonalize, we find E versus Kx and Ky because we're in 2 dimensions, and we find that there are 6 points in the Brillouin zone where the energy goes identically to 0. And these points are called either the valleys of graphene or the Dirac points of graphene. People use these 2 concepts interchangeably in the literature. So now, what I should point out is that every 2 of these points are inequivalent. The points that appear in yellow are equivalent because they are easily related by a rotation. However, the K and the K prime, which are the ones that I'm interested in, are inequivalent because they are related through time reversal. So you see, so all the K points are related by simple rotations, while K and K prime are related by time reversal. So why am I interested in these 2 points specifically, or these values? Because after diagonalizing my Hamiltonian and expanding my momentum close to this 0, close to the K and K prime point, I find an equation that we kind of recognize from relativistic quantum mechanics. We find a Dirac-like equation for the electrons at each valley. Basically, my momentum disperses linearly with energy. Near the Dirac points, graphene is effectively described. The low-energy quasi-particles of graphene are described by this equation. Tau z tells you if you are at the K or K prime point. So that's what we call sometimes the isospin. Sigma x tells you about the sublattice, that A and B that we talked about in the beginning. So if you're in sublattice A, bases of your spin are A and B in this case, instead of up and down. It's a pseudo-spin, it's not a real spin. And sigma y, of course, it's the Pauli matrix that describes also the pseudo-spin. Now, what is very interesting about this Dirac-like equation, if you notice, the Fermi velocity, or the velocity at which these electrons move, is the speed of light over 300. So we have effectively relativistic electrons in a material, relativistic quasi-particles, that do not move even close to the speed of light. And this is what's so fascinating about this quasi-excitation or quasi-particles in materials, specifically in this new type of, let's say, 2D materials. One more important property that we know also from high energy is that massless quasi-particles are helical, right? So now in this case we call them, they are pseudo-helical. So basically I have a coupling, I have a conservation of the coupling between the spin, or the pseudo-spin in this case, and the momentum. So that means if I'm moving forward, I should have a spin for the purposes of this that's pointing up. And if I move backwards, I need to have a spin that should point down. In this case, it's a pseudo-spin, not a spin. So that means that if I find in my material a potential obstacle that does not lead to the flipping of the pseudo-spin, my particle will keep going without noticing even that obstacle. And that's what's known as Klein tunneling in graphene. Okay? So this has been experimentally observed. And that's due to the conservation of pseudo-helicity in the case of graphene that does not allow your particles to backscatter due to simple potential scatters. So if you want your electrons in graphene to scatter backwards, you need either to mix the valleys, so have very short range impurities that could have a large momentum transfer, or you should have an impurity that leads to the flipping of the pseudospin from A to B. Okay? Good. So Dirac materials also exist in 3 dimensions, and this is where I'm going to give a very short description of topological insulators. So topological insulators really changed the paradigm of our classification of materials. So as you know, we classify materials as metals, insulators, semiconductors, and so on and so forth. But then topological insulators appeared, and we discovered that we were missing a lot in our classification. This classification is more general because we need to know the hidden topology of the electrons in my material itself. So it's not enough to look at the simple symmetries. I need to look at the topology of my fermion and the way it evolves across the Brillouin zone. Different topological states. Why is this important? Why do I need states or condensed matter states or different states of matter with different topologies? If we assume that vacuum has a trivial topology and the topological insulator has a non-trivial topology, as soon as I terminate my topological insulator, I should have a conducting state with a reduced dimensionality. I'm going to clarify this in what comes next. Okay, so for all practical purposes, from the old classification, if I look at this and I look at that, I say this is an insulator and this is an insulator. There is a gap large enough. By looking at the dispersion, I say insulator and insulator. But that's not enough because I'm neglecting all the topology. If I look, for example, at the valence band, and I look how my spin evolves across the Brillouin zone, I notice that in this trivial insulator, my spin does not change direction as I move. If I look at the topological insulator, I notice that I start with a spin up, and then as I move, there is a spin flip. Then I measure a very famous number that is called the Chern number, or for those of you that are used to more real space quantities, the Schermion number, in, I think, high energy physics, the Schermion number, right? You find that this has a different Chern number than this one. This may have a 1, this may have a 0, right? So they are 2 different topological states. So if I put this insulator next to this insulator, a surface state should live between them. So this may seem as nice math and nice theory, but they exist. So they have been found, topological insulators have been found in the family of bismuth selenide, bismuth telluride, antimony telluride, and these materials are usually made through quintuple layers that are strongly bound, and then each quintuple layer is coupled to the next one through van der Waals. So they are still materials that can be exfoliated, right? Because you have van der Waals. So every 5 layers are strongly coupled and the other ones are weakly coupled. They can be stacked. As we said, we have the valence, the conduction band, but what we were missing before was that there is a surface state that's a massless state. It's described by a massless Dirac equation, and these states have a definite helicity on the surface of the topological insulator. So this was verified through ARPIS, which is angle resolved photoemission spectroscopy. Okay, so when they go and they do this, they notice that there are massless states that live at the surface, only at the surface, and are helical state. As we said, these helical states, that means that there is a spin momentum coupling and that the state is massless. Okay, so both aspects, the presence of this state at the surface and also the helicity of the states, were experimentally verified through these experiments. To give you a picture of a topological insulator is simply an insulator in 3D and a conductor in 2D, as long as you terminate it. Okay, so this state lives only at the surface due to the change in topology between the topological insulator and the trivial vacuum that we have. Why do we care about all of this, right? So as you know, we live in an age of information. Some of you may remember this type of computers that we had at home, and most of us nowadays, we have this type of cell phones. This cell phone is way more computationally capable than this computer. That means that we were successful at doing something in material and condensed matter physics. We were very successful at miniaturization of things. What was the aspect of miniaturization? It was reflected on both aspects of information, because if you have information, you need to process it and you need to store it, right? So these are the two aspects of information. What did we miniaturize? The transistor. So this is the first transistor that was built in Bell Labs. It has the size of a toaster. Nowadays, in a typical processor, right, you have in 47K millimeters squares, you have 1.2 trillion transistors. Now, if you go to the GPUs, which are even better, you have 2.1 billion transistors in 800 millimeters squares. So with all certainty, I can tell you that the transistor is the most manufactured device in history. There is no other device that has been manufactured more than the transistor in history. This is the processing aspect. So we were successful at miniaturizing this. Now, the second aspect is the storage. This is a very old hard disk. To move this, people needed to have a truck and few people moving it. And the storage capacity of this was 3.5 megabytes. You could have a pocket-sized hard disk that has 20 terabytes. The technological advancements make things smaller. But the problem is that we're hitting certain limits. We're getting so small that we're hitting certain quantum limits. My transistors are facing problems, right? Because the smaller you get, the more quantum effects you will have, and the more tunneling of electrons, and so on and so forth. So now we need to find smart ideas to tackle this problem. So we cannot depend on miniaturization forever. One of these fields that aims at solving this problem is called spintronics. So until now, the electronics have been depending on the electronic charge of electrons, right? So I either have charge 1, I don't have charge 0. But we should remember that electrons have a spin. So in addition to charge, no charge, I could have a spin up and a spin down. So basically the field of spintronics is the field that aims at utilizing both the charge and the spin of electrons in applications, in what is known as spintronic devices. As soon as we talk about spin, magnets and the spin orbit coupled materials are things that come to mind immediately. As an example that I'm going to give today is the transfer of information between magnetic layers. If you have a ferromagnet separated by a non-magnetic material, usually a metal, and another ferromagnet, you can make these two magnets communicate with each other through an interaction that is called the RKKY interaction. Okay, and this will be the focus of the next part. This magnetic exchange is mediated, just for me to clarify, through the non-magnetic basically through the electrons of the non-magnetic material that's in between the two ferromagnets. Let us see what is the RKKY interaction. Actually, this RKKY interaction had its beginnings in nuclear physics and not in condensed matter physics, but then the condensed matter physicists took it and they saw, oh, this explains what we have. So the beginnings of this interaction was in nuclear physics. So the indirect exchange mechanism between local magnetic moments is called the RKKY interaction. What do we need to have an RKKY, or an indirect magnetic exchange? We need a Fermi gas. For simplicity, let's take a two-dimensional electron gas as a simple example. This is a p square over 2m type of material, a free electron gas. Then, in this free electron gas, we need to have a Fermi level. Basically, I have the occupation of the bands is up till here, and then I have a Fermi surface. So the electrons that usually cause the conduction and all the dynamic phenomena, the dynamics in my materials, are the ones that live at the Fermi surface. And these electrons are usually a spin degenerate. I have as many up as I have down. So then what I need to do is to add some magnetic impurities in a dilute way, and I assume that they interact via their magnetic moments. So let's ask the main question. So the main question that we're asking here is, what happens if I add one more spin to a metal? How will my metal react? I have a metal that's a spin degenerate, very nice. Every electron has its pair, every spin up has a spin down, and then I come and I add one more. I have this two electron gas, I add the spin S1 at the location r equals 0, and the electrons with small si, the electrons of the metal, will locally couple to that big spin that I have. So my S1 will couple to the spins of the metal locally through a local exchange Hamiltonian that is called the SD Hamiltonian. The J is the exchange coupling strength that we have. If we look at this local exchange interaction that we have, and we compare it to an interaction that we know, which is the Zeeman coupling, we can notice that the electrons, the small si's, effectively see a magnetic field due to the presence of that magnetic impurity, right? And the effective magnetic field is proportional, of course, to the strength of the additional spin that I added. So the electrons in my metal are seeing an effective magnetic field due to the presence of a magnetic impurity. As we know from electrodynamics, if I have a magnetic field, I will have an induced magnetization. And that magnetization is dependent on the spin susceptibility. So that means that if I take that effective magnetic field, I can perform this integral in an easy way because there was a delta function, if you remember there. So then I have an effective magnetization that is generated, and it's proportional to the real space representation of my spin susceptibility and the additional spin that was present. Okay, so now an induced magnetization will lead to the induction of a spin density in my metal. So this spin density, if I compare both formulas, is directly proportional to the first impurity, the external impurity, and the spin susceptibility of the metal. To summarize, if I add an additional magnetic impurity to a metal, there will be an effective magnetic field felt by the electrons of the metal. Then the electron gas will respond by generating an induced magnetization and consequently an induced spin density. Okay, so this is what happens. So in a cartoonish picture, assume that I have a spin S1 that is added at the origin. This will lead to the generation of a spin density. Then, if I put a second spin at a distance r, since this spin density will be oscillating and decaying, then here I have a majority of a spin up, then this electron will be tried to screen these spins here and will be pointing down. If I add a spin up, an additional spin at this location, this spin will be pointing up because it will try to locally screen the additional spins that I have, which are in majority down. Okay? If I have two spins separated by the distance r, they will see each other, spin 1 and spin 2, the two external spins, they will see each other through the spin density oscillations of the bath that are proportional to the real space representation of the spin susceptibility of the metal. Where do these oscillations come from? If you make the simple exercise that you did either in thermal physics or solid state and you calculate the spin susceptibility of a two-dimensional gas, electron gas, you find that this d is the density of states, that this susceptibility is constant and it's the Pauli susceptibility up to a number q. Q here is the momentum transfer due to scattering, up to a number q that is equal to twice kf. And then the behavior of this function changes. So we have a point of non-analyticity at twice k Fermi. Twice k Fermi is the largest Fermi wave vector that traverses my Fermi surface, right? My Fermi surface had a radius that is twice k Fermi. So now as soon as I exceed twice k Fermi, it's harder for my electrons to respond to the external spins, and therefore the spin susceptibility is going down. But now this point is of interest because this point has a non-analytic behavior in the spin susceptibility, and this is called the cone anomaly. So what we should remember here is that the cone anomaly is the largest vector that traverses our Fermi surface. Okay, it connects two maxima in my Fermi surface. Here I have I have a circle, therefore any 2 points can represent a maxima, but it's twice kf what I have here. So that means that I can define the RKKY interaction through the magnetic exchange coupling, I make it a function of R, and if I plot this magnetic exchange coupling, I see that it starts at a maximum and then it oscillates. But what's the meaning of this? If this number, my JRKKY, is positive, that means that my electrons are antiferromagnetically interacting with each other. My J is in the negative side, then my electrons are ferromagnetically interacting with each other. And the period of oscillation of this RKKY is proportional to twice K Fermi, which is the Kohn anomaly. So twice K Fermi can give you a wavelength of the RKKY oscillations, and the power of oscillation depends on the dimensionality of your metal and the type of electrons that mediate this type of exchange. So if you have Dirac fermions, it will be different from regular Schrodinger electrons. Okay? So what we should remember is that the Kohn anomaly determines your period of oscillation. Okay? So, and this is the RKKY. So now we have a phenomenon such as the RKKY. And we want to control it to make our hard disks better. We either go and we discover new materials, we start finding topological insulators, two-dimensional materials, vial semimetals, all the new and hot topics that we have in condensed matter, or we can say we already have materials, so let me try to control them via external probes. Okay, let me try to periodically drive them through light or other periodic drives and change their properties. Okay, and this will be the focus of the next part of the talk. So I'm going to talk about periodically driven systems and how I'm going to control the RKKY through this type of periodic drives. So let us remember that if I have a solid that's monochromatically driven by a laser, then in the typical picture that we learn in graduate or undergraduate solid state, with weak laser fields, what I have is a weak perturbation of the occupation between the bands. I'll have few electrons excited from the valence to the conduction. I use linear response theory and I'm fine. Yeah, that's good for weak fields. But now, if I have a strong laser fields, that's not the picture anymore. I have a strong band renormalization due to photon dressing, and I have a large electron population redistribution. So I cannot use perturbative methods anymore. I should use non-perturbative methods in order to describe what's happening in my system. And this was firstly shown in this paper here, where they show that in a semiconductor, if you subject it to a very strong light field, then the bands will renormalize strongly. Here they open the gap due to the presence of this strong laser or the strong light field or laser field, right? So it's not enough to say perturbation theory and linear response will work here. So more recently, with the appearance of both Dirac materials and two-dimensional materials, Floquet topological insulators have been experimentally verified, and the appearance of an anomalous Hall effect in graphene has been also verified, and all these effects are simply due to light. Okay? So you can change even the topological nature of your material by simply subjecting it to a periodic drive. And that's what we call Floquet engineering. So you have graphene is a regular semi-metal, you subject it to light, okay, then a gap opens, then you see that this insulator became an anomalous Hall insulator, and you will have the circulation of an edge state. This is what we mean by a Floquet Chern insulator. Okay? So now the question is, if I have a magnetic lateral heterostructure, so meaning I have a left ferromagnet, right ferromagnet, and a two-dimensional electron gas, we know that the magnetic exchange will be mediated by the electrons in my two-dimensional electron gas via the RKKY interaction. And the exchange, as we saw in the previous slides, depends on the Fermi surface properties and the distance between the two ferromagnets. So now you may think this is very inconvenient, because every time I want to change the RKKY, I either need to change the material, or I need to make this longer, which means I need to create a sample every time, right? But what we suggest is that since the irradiation of this two-dimensional electron gas can lead to the renormalization of the equilibrium bands and the formation of the Floquet block states, then we may have a way to control the RKKY interaction just by means of subjecting it to a light. So let's see, if we have an irradiated two-dimensional electron gas, what we do is that we capture the light matter coupling via minimal coupling. Here tau means time, by the way. And this is the vector potential that describes a circular polarized light. So now we have a Hamiltonian that is driven, and the function of time here is a periodic function in time, which is essential to what comes next. So if we have a Hamiltonian that is periodic in time, Floquet theory ensures that we have a solution to the equation such that this solution takes this form. Okay? And here, epsilon Lk is called the quasi-energy because now we have a time-dependent system, and the phi's are the Floquet states, which are states that have the same periodicity as the periodic drive that we have. So, using the Fourier representation of my Floquet states, I can plug this back into my Hamiltonian, so I get rid of all the time dependence that I have in my Hamiltonian, but I trade it off by a very big sized matrix that contains all the light matter interactions in frequency space. Okay? So for example, let's see what happens in the two-dimensional electron gas. So as soon as we irradiate the two-dimensional electron gas, we have the formation of the different Floquet bands. There are certain features in this Floquet band. So this N0 was the equilibrium-like band, the original band that existed, but now as an average in time, there will be the quasi-energy means the time average energy. So the time average energy will lead to the appearance of new bands, and these bands are separated by h power omega. So these bands here means the bands that are present due to a photon absorption, and these bands down here below the equilibrium band are the bands that appear due to photon emission. Okay? So in addition to the appearance of the different replicas, another effect that's important is the appearance of a potential shift. So basically my original equilibrium-like band, which is the n equals 0 band, will be shifted by a V2. Okay? So, and this will play a very important role in what happens next in this type of systems. So let me just summarize here. This is just for the theorists, and if you're interested, let me know, and I can discuss with you in the next slides. If I want to find the time average magnetic exchange coupling between my two ferromagnets, so now I need to use something called the Keldysh-Floquet formalism, so which relates the magnetic exchange interaction to the time average spin susceptibility. Now, here just this constant has the left spins, the right spins, and the area of the 2D unit cell. These are just constants, but the time average spin susceptibility is given in terms of the retarded, lesser, and advanced Green's functions that appear naturally from the Keldysh-Floquet formalism. Now, the most important of these quantities is G lesser, because G lesser also captures the effects of thermalization in my system. So I have a system that is constantly irradiated, and I need to achieve a non-equilibrium steady state through the Floquet picture. So that means that there should be a mechanism of thermalization. This could be either the coupling to the fermionic bath, which are the metallic leads, or the coupling to a bosonic bath, which is the phonons in my material. So in this case, what we choose is a fermionic bath, and here this sigma is the self-energy of my fermionic leads. Okay, so this way we achieve thermalization. And through this formalism, we're able to find the time average magnetic exchange between these two ferromagnets. We have two main regimes. If I have, let's call the V2, the shift, let's call it delta for now. So if I have my E Fermi larger than delta, I have a certain regime. And if I have my delta greater than E Fermi, basically, if my E Fermi is less than the shift, this is one regime. And if my E Fermi is less than the shift, then I have a different regime. So let's start with the first regime. So as we can notice, at equilibrium, which is this light blue color, we have the regular spin susceptibility that we know. Then if I start increasing my light matter coupling strength, what I notice is that I have a deviation from the equilibrium susceptibility and the appearance of new cone anomalies in my system. So what's happening? Remember that now I have all the Floquet bands. They appeared. So in addition to the equilibrium-like critical or spanning vector, right, I have the possibility of additional spanning vector. So I could have the spanning vector of the second band, which is a Floquet band. And I have the possibility of this spanning vector of the n-2. And in addition to intraband, I could have interband transitions. I could go from the, let's say, 0 to the 1 or 2 to the -1. So I could have transitions between all these bands. And these are the additional cone anomalies that are appearing in my system. I think that I should mention is that the occupation of the Floquet bands is always in sequence. Basically, the one that's mostly the band that has the highest occupation is usually the equilibrium-like band, and then the other bands are occupied, but not as much as the equilibrium-like. Okay? So now if I see the magnetic exchange, what I notice is that my magnetic exchange is dominated by one of the cone anomalies. And that's the cone anomaly of the band that has the highest occupation, which is the equilibrium-like band. And then as I increase the light matter coupling, I can notice that my period of my RKKY is increasing. And when I have a very strong light matter coupling, I have a small modulation due to other periods. Okay? So that means that if I have a strong light matter coupling, then I will have a longer RKKY period. And this period is usually dominated by the zero Floquet band, which is the equilibrium-like band. And this period, as we can notice, I'm increasing the light matter coupling and it's becoming longer. But this cannot go forever, right? And that's when I hit the second regime. My delta, the shift, becomes larger than my Fermi energy, right? So if my delta becomes larger than my Fermi energy, that means that the band with highest occupation, the n=0 band, migrated above my Fermi level. So now it will not contribute to the dynamics anymore. What happens is that the cone anomalies that appear are the cone anomalies of the lower bands that have less occupation than the band I migrated above the Fermi level. If I see my exchange interaction, I notice that it's simply decaying and it never changes sign. And this is due to the weak occupation of the additional Floquet bands that cannot lead to the changing of the sign of the interaction. Basically, it cannot lead to clear RKKY oscillations. And this is logical because this decaying behavior that we have is similar to the RKKY at equilibrium when we have an insulator mediating the RKKY. So what this is telling me is that my bands are so weakly occupied that my system behaves almost as an insulator at this regime. We can draw a phase diagram. Basically, this is the light frequency and this is the light amplitude. And what we can notice is that in this regime, without changing the width, this is important, without changing the width or changing the material, I can change the interaction between the left and right ferromagnets from antiferromagnetic to ferromagnetic and so on and so forth. I don't need to change the width. I just change, for example, the light amplitude, or I change the light's frequency, okay? But then we should be careful because if we keep increasing along this line, there will be a regime in which my system becomes almost as an insulator because the main occupied band will migrate above the Fermi level. At this point, I cannot control this RKKY anymore, and whatever was ferromagnetic remains ferromagnetic forever. We can control the exchange coupling. We have a certain regime in which we can control the exchange coupling, so we don't need to change the R, basically the distance, or change the sample. We don't need to build a new sample, we just need to use different light matter parameters. And we have a light-dependent period that, of course, it's inversely proportional to the difference between the Fermi level and that shift that was caused by light. So in this part, we have seen that we can indeed control the RKKY interaction mediated by a two-dimensional electron gas due to the formation of this potential shift that leads to the changing of the main spanning vector, that twice kf, that controls the RKKY. We have the appearance of new cone anomalies, and we have two main regimes. One regime in which I can control my RKKY, and one regime in which my RKKY becomes almost as the RKKY controlled by an insulator. So yes, light can control these things with no need for us to build new samples. Okay, so that was the main part of this, the main message of this part. So now, as you noticed, whatever I said before was for spinless electrons, meaning I didn't have any spin-orbit coupling. And all the interactions, the RKKY interactions that happen were collinear type of interactions, meaning S dot S. I didn't have any non-collinear, meaning S cross S type of interactions. So now the question is, can I generate non-collinear interactions just by simply shining light on a material? Okay, but for that we need to introduce something called the Rashba semiconductors. So for this, I'm going to use this material, which is bismuth telluride iodide, and as you can notice, these are asymmetrically stacked triangular lattices. Now, if you flip this top to bottom, you will not recover it again. That means that this has an intrinsically broken symmetry along the C-axis, basically along this axis. I don't have a symmetry. And that means that I have a net polarity along this axis, and that causes the appearance of a spin-orbit coupling in the plane. Okay? So in the plane of my material, in the AB axis, which is the XY, let's call it, we have a spin-orbit coupling. So now, if we diagonalize, we use density functional theory or K dot P theory, we find that the low energy electrons of my material live at this point that is called the A point in the Brillouin zone. Okay, so these are the low energy electrons of my material, and they follow this effective Hamiltonian, which is simply a two-dimensional electron gap, a two-dimensional electron gas with two different effective masses and a two-dimensional spin-orbit coupling in the plane, in the XY plane. Okay, so now if I plot the Fermi surface, now things are three-dimensional. We went from 2 dimensions to 3 dimensions now. So now the Fermi surface is really a volume, right? It has a volume, not only an area. So we notice that we have an inner and an outer portion of my Fermi surface. So what's the difference between the inner and the outer portion? The inner portion and the outer portion are characterized by their helicity. So the inner portion has, let's call them left helical electrons, and this one, the outer one, has right helical electrons. So they are electrons with different helicities that exist in the different portions of your Fermi surface. Good. So both helicities exist between the points KD and minus KD, basically in between here and here. But when as soon as you exceed the 2 Dirac points that we call them, you will have only one helicity. And that naturally will lead to an asymmetry in the spin susceptibility that we will notice next. So the chi XX and chi YY may be equal, but they are not equal to chi ZZ due to this asymmetry in the helicities of the two portions. Let's assume that we get this material. We put a 2-dimensional ferromagnet on top and bottom of the material. So that means that we're going to mediate the RKKY interaction through these fermions of bismuth telluride iodide. We can find the magnetic exchange simply by integrating the magnetic susceptibility. And in this calculation, since we have periodic boundary conditions in the xy direction, the RKKY simply depends on the momentum transfer across the direction of the stacking of the ferromagnets. Okay? So the only scattering processes that contribute to the RKKY are the ones in the z direction. Okay? So, and the magnetic interaction is limited to collinear spins. Now you will say, wait, but I had a spin orbit. A spin orbit interaction was in the xy plane, right? So, and the magnetic exchange is mediated by the scattering processes that happen along the z. Along the z, I have a simple Fermi gas. I don't have the spin orbit interaction in the z. I only have it in the xy. That means that I only can couple ferromagnets. When I say collinear spins, I mean I can only couple ferromagnets with either parallel or anti-parallel directions, okay? The spin susceptibility, as we said, is anisotropic between ZZ, XX, and YY, and the interlayer exchange, the magnetic exchange interaction between these ferromagnets, has only Z, ZZ, XX, and YY. Basically, only collinear spins can talk to each other. If we irradiate the material and we focus on the high frequency regime, we can obtain a stroboscopic Hamiltonian, basically an effective Hamiltonian that describes what's happening to my fermions. So as you can notice, in addition to the typical terms that we had before, the spin orbit coupling, the k square in the z, the k square in the x and y, we have the appearance of the potential shift, like in the two-dimensional electron gas that we saw. But in addition to that, we have a third term, which leads to the opening of a gap in my spectrum. Okay? So previously I had these Dirac points, KD and minus KD. These points are going to be gapped, and the size of the gap is proportional, of course, to the light-matter coupling that I have. So I go from this type of picture at equilibrium. I do my light driving. As you can notice, the shape of the Fermi surface changed. And that's because two main effects. The Fermi surface will become smaller because the potential led to a shift, making it smaller. And more importantly, it will lead to the opening of the gap at this Dirac point and this Dirac point over here. Another very important effect, at equilibrium, the spins are only in the plane, in the xy plane, right? I had spins only in plane, but as soon as I irradiate my material, I also have out-of-plane components across my Fermi surface, right? So that means that whenever I irradiate this material, I will have a photo-induced non-collinear magnetic exchange, meaning off-diagonal elements in my spin susceptibility tensor that will lead, in addition to the collinear terms, to an irradiation-induced non-collinear term. Imagine that you have a ferromagnet with a spin up and a ferromagnet with a spin in the x direction without light. They do not talk to each other, but as soon as you shine the light, they magnetically couple. Okay, this is what I mean by non-collinear magnetic coupling. All right, so as we said, things depend on the critical spanning vectors, or the different vectors that traverse the Fermi surface. Now my Fermi surface is a bit more complicated, right? So I have multiple of them. So I have these two maxima that could be connected, these two that could be connected, and this one that can be connected here. When I plot my magnetic exchange, for example, the ZZ part, I have the typical period modulated by the additional spanning vectors, which are the Z minus, the minus plus, and the Z plus. And if I plot the non-collinear term, I see that it's non-zero, and it depends only on this term over here, which means that I have a very long period of oscillation. So with this, we have seen in this part that the most important part is that we can generate a non-collinear exchange uniquely due to the presence of an irradiation field on a material. So I can generate couplings that were not present just simply by irradiating my material. So now I would like to end with some just highlights about space-time dependent systems that are the current research that is done in my group. So for example, whenever I irradiate an insulator and I have the crossing of one of the bands the valence band to the conduction band, I have the appearance of what is called a Floquet topological insulator, but we can also show that we have the appearance of vortices in a similar way to what we have in superconductors that have a magnetic flux traversing them. And we can also generate higher order topological insulators by irradiating them with something called a bicircular light, which is a light that has two frequencies, and one of the frequencies has an integer ratio of the other frequency, and it leads to the break-in of space symmetries, the gapping of the surfaces, but then it leads to the appearance of hinge modes instead of surface states. And with that, I would like to thank all my collaborators at the different places, and I would like to thank you for your attention.
For the interesting talk. And do you have questions?
Oh, yes.
Yeah, I had a question. It looked like, this was early in the talk, I think it was slide 6.
Okay.
Where you showed a Hamiltonian. It seems to be symmetric in X and Y. Why not? I thought they were directional.
Ah, good. That's a good question. Thank you. Okay.
L in front of the X, I believe.
Yes. That's a choice. Yeah. You mean here, right?
Exactly.
Yes. Okay. That's actually a very good question. So, whenever you have the hexagon in real space, if you start solving with the, do we have a board? We don't have a board. Okay. So, if you make, so there are two ways to draw the hexagon, right? So you either put 2 points vertically or 2 points horizontally, right? Okay, good. So if we start in real space with the 2 points here horizontally, then in momentum space I will have them vertically. But if we start with the 2 points this way, then in momentum space I'll have this way, right? So as we said, the choice that I made in the solution of this in real space was this. So that means that in momentum space, the k and k prime points are connected across the horizontal. Now, remember that in a Brillouin zone, whenever I go here, I go back from the other side. So that means that whatever goes across the x direction will go back to the minus k, and that's what the tau captures, but not across the y. And that's just simply a choice of the way you oriented your lattice. You see, that's a kind of time reversal. It kind of captures time reversal in the system.
Time reversal is only in the X, not in the Y direction.
Yes, because...
Well, here's the thing that was bothering me. What is X and what is Y is in my head. It's not it's not anything physical. I could change it.
Yes, this is okay. Don't forget. Okay, good. This is a good question. Actually, I wish if we had a board, but fine. So whenever you make a choice of the orientation of your lattice in real space and you solve it, there will be an orientation of your Brillouin zone, right? So as soon as, by the way we chose this representation, the way your k and k prime points are represented are through the changing of only the kx, because the gamma is in the center, then you have the k point, which is the edge of your Brillouin zone, then as soon as you move a little bit, you go back to the k prime. So that means that the x and the minus x, kx and minus kx are the ones that are connected. Now, I could change this representation just by a simple rotation, and they have the tau connecting the x and the y. That's also a choice. Nothing changes. You just rotate your Brillouin zone, which means you rotated your lattice in a given way. But this is just a representation. So, but again, no, this is very important, because as soon as we chose the representation in real space, we should always remember what we chose. There is a lot of mistakes that could be done if we forget what we did in real space.
I would have made that mistake.
Okay. No, but that's an excellent question. Thank you very much.
I was wondering, how do the properties of the material help you overcome the problems with the miniaturization and the scaling of the information process?
If in addition to the charge, you have a spin, so that means you can handle way more information. So if you assume that you could make a new transistor that could rely on a spin, okay? So you could handle maybe 2 times more information in this type of transistor, And that way you don't need to miniaturize more because the same size system can handle more information. So this is what we aim at. That's not the only aim. There is topological insulators that specifically have helical states that have very specific spin momentum coupling, and that also help us in reducing the heating, because as we said, these helical states do not backscatter, which could cause extra heatings, right? So if you could avoid that problem too, that's also a good thing to avoid. So you see, it depends which side you're looking from the side of heating, the side of information. So there is advantages depending on what you want to do.
For these devices, you need to constantly shine light on it.
Huh?
For these devices, you need to constantly shine light.
If we are going to go the route of the Floquet engineering, we need to shine light. Yes. So, but again, shining light, you see the point here, shining light is easier than to build a sample. So, yeah. So, yes, that's another thing. You can control them via light, as we said. Instead of building a new sample, you just simply shine light, intense enough, and hopefully you can obtain an additional degree of control.
Disclaimer, I'm an astronomer, so I may not be catching all the details of the solid state stuff, but you're mentioning that essentially those devices need to be controlled or need to be triggered by light shining on them. Now, is that a problem if you think about ambient photon radiation? So I'm thinking about a device like this that would be used in space where you might have gamma rays, X-rays, and all sorts of radiation. Would that affect the stability or performance of the device?
Let me be clear. This is still at the experimental level on Earth, which means we are still operating at very low temperatures. So all these Floquet type of applications that we have seen, for example, this observation of the Floquet topological insulator, which is this one, and the observation of the anomalous Hall effect in graphene due to light irradiation have been observed at low temperatures, because periodically driven systems also have problems that we need to overcome. They are not there yet. There are problems of internal heating because you're constantly pumping energy into the system through your light, and then you need to overcome that through what we call bath engineering. So how does your system achieve a non-equilibrium steady state the fastest way possible? So I think it's too early to send them to space. I don't know what will happen. Yeah, but assuming that we could send them to space and that the space is very cold, right? Cold enough to keep the stability of this. So then having external radiation like gamma rays, they are very highly energetic. Oh, but the intensity, okay. So if it's high energetic, okay, assuming that that irradiation does not damage the material itself, as long as it's not intense, I'm okay.
How about some environments on Earth? Because it's easy enough to shield light from the system, but to shield a system from ambient X-rays. So I'm thinking about medical devices. For example.
No, I think
you have any kind of medical equipment where you might have X-rays leaking from a radiation device or anything like that.
I think
disable the system.
I think as long as that light is not intense, we're okay. Yes, this depends on intense light. The light should be intense, very intense. Otherwise, we don't change that. Yeah, we need a strong laser fields. Basically, a strong means the ratio of the electric field amplitude to the energy of the photon. Okay, so if that ratio is small enough with that ambient radiation that you have, then it does not affect it. But it depends on the E0, basically the amplitude of the electric field is in the numerator. So if it's not intense, you're fine. Mm-hmm.
So Mahmoud will be available at 6th floor conference room after the talk. So if you have your questions, then you're welcome to talk to him. Let's thank Mahmoud.
Thank you very much.